In these sections, I'd like to explain how to express the Ampere's law in the differential forms. But first of all, I'd like to explain the Green's theorems in the planes. Consider a region R be a surface bounded by a closed curve C. So we consider xy planes. Curves AEB and BDA are expressed by the y equal fx. This is AEB. BDA is expressed y equal gx. Then we'd like to consider the double integral of the round p over round y. And p is a function of x and y. Then this is double integral is integral over x and the integral over y. If you consider the integral over the y, from the lower limit is f and the upper limit is g. It's coming from here. If you integrate of this part, becomes px g minus p x f. So this negative sign, second terms is here. And this first term is a pxg is a positive. But by changing the lower limit and the upper limit is a b a. A to the b is changing to the b to the a. You add a negative sign. We can combine these two equations to express the integral p dx over the c, because following this path from the a to the b, and from the b to the a, and the y becomes a g following this path, and return to the a. So it's expressed p dx. And similarly, if you consider the integral of the round q round x, you can express the integral of the q dy. So from these equations, you can express the round q round x minus round p round y is expressed p dx q dy. So we call that this is the Green's theorems in planes. Then I'd like to introduce the curls. Curl of the vector quantity A. A is a function of the x, y, z is defined. Curl A is a vector product of the del operators. This is del operators. Cross. This is cross product. And a vector A. So this is del operators. Cross. This is cross product. And A vectors. It becomes E sub x round A sub z round y minus round A sub y round z. This is the x component of the curl A. And the y component. This is the y component. And the z component. Following the cross product. The example of A is equal to the R. If you want to find out the x component of the curl A, so if you want to find the curl A x component, so this corresponds here. For the A sub z, you can substitute z. So this is z. A sub y, y component, y. So each term is 0 actually. Partial derivative of z with respect to y is 0. Partial derivative of y with respect to z is 0. So x component becomes 0. So we could use the same calculation to find the curl A. It becomes 0. So actually curl R is 0. We derived these equations. Okay, this is a definition of curl. Then I'd like to explain the Stokes law. Let S be a surface bounded by a closed non-intersecting curve C. This is the curve C. And N be a unit vector normal to S. Unit vector normal to the S. So this is n vector is a perpendicular with respect to the areas. When the surface S is expressed z equal fxy. F is a function of xy. Then from these equations you can express the use a capital F is a z minus fxy equals 0. So we can use this either expression to express the surface area of S. Then unit vector normal to the surface is given by nabla. Del operator F divided by the magnitude of the normal vectors becomes a unit vectors n. And del operator F becomes, so this is the del operators round F round X, round F round Y, round F round Z. This expression is expressed minus round lowercase of the F, round X, X component, minus round F round Z, E sub Y, Y component, plus, so this becomes just 1, derivative of the Z with respect to Z is 1, so E sub Z, and then divided by magnitude. This is a unit vector n. Therefore, we have a n dot dy. This is scalar product. Becomes, actually this quantity, it becomes minus round f round y over square root 1 plus round f round x squared round y squares. This is equal to this quantities. Also, f equals z equals these equations. You can express the minus round z round y n dot ez. You can express this way. Then now considering the following equations. Del operator, cross product. This is a curve. And then first component a sub x, e sub x dot surface integrals n ds. N is a unit vectors perpendicular to the surface ds. Then for the curve, use the definition of the curve. You can express these equations and these expressions. These expressions substitute is here. Then use express the n dot e sub z. This is the common factors n dot e sub z. Then this becomes, you have extra terms, it's here. Then if you look at this inside of the parentheses, this is exactly equal to this equation. Round a sub x round y plus round a sub x round z times round z round y. And a sub x is a function of the x, y, z. And but z is a function of the x, y can be expressed. So if you substitute z equal f x, y, so all the a sub x is a function of the x and the y only. This left hand side, if you use a capital Z, is equal to the round z round y. So these terms can be expressed using the g. It becomes these equations. And this corresponds to dx dy. This area is a ds. So this is thetas. This is also thetas. Then you can express the ds cosine theta is expressed dx dy. For the right hand side, we can apply the green theorems. This becomes g dx. So return to the g is actually equals to the a sub x. This is a sub x. And substitute a sub x. It becomes a sub x dx. Similar method we can apply to find out this terms. It becomes a sub y dy. This becomes a sub g dg. So if you combine all the terms, it becomes this right hand side becomes a sub x dx plus a sub y dy plus a sub g dg. This is expressed with a scalar product a dot dr. So we have a very important equations formula. We call that this is Stokes theorems. Stokes theorem convert from the surface integrals ds to the line integrals dr. Important theorems to convert from the surface integral to the line integral. Then we could find the differential form of Ampere's laws. Integral form of Ampere's law is expressed this way. And the right hand side is I enclosed is use current densities is expressed I dot n ds integrate over the surface. So this is the expression with the right hand side. And the left hand side, we can apply Stokes laws from the line integral to the surface integrals. In this case, the line integrals convert to the surface integrals. So by actually these two equations is exactly the same. Then if you look at the inside of this part, is this times here. Actually, these equations have to be satisfied independent of the size of the surface. So curl B should be equal to the mu sub 0 I. This is a differential form of the Ampere's law. Okay, this is the end of this session and also the end of today's lectures.